In the last unit, we introduced the definition of the derivative. And remember, that was the distinction between a secant line and the slope of that secant line versus the slope of a tangent line. Just to quickly review that, let's take a look at how that would be interpreted in various graphical scenarios. If we look at a secant line, then it's something that's going to give us the average rate of change. And notice the keyword average in all these points here for some function over some interval delta x. And again, that's built on the construction of 2 points. We have 2 points and we can connect those with a straight line. Then somehow we have the 2 points involved, and the averaging between those 2 points over those 2 points is part of what goes into a secant line. If we get more specific and talk about a graph of position against time, then we get velocity. If we talk about a function of velocity, then the secant line will represent acceleration. We can make that a little more concrete by looking at some specific examples. If we looked specifically at a graph of velocity against time, say doing something like this, and we pick 2 points on it, and we connect those 2 lines, then the secant slope, or the slope of the secant, is going to be defined by the rise over run. In this case here is the change in velocity, or meters per second, change in meters per second, divided by the change in the units down here, change in time, in seconds. And as soon as you recognize that those are the 2 building blocks for the slope, then we can talk about the ratio, change in v over change in t, and the units for that will be meters per second divided by seconds, or meters per second squared. So that'll give us units of acceleration. If we talk about a secant line, how much velocity did I change, or how large is my velocity change over this certain time interval, we're going to get an average estimate of the acceleration, and the units indicate that. If we look at the second example and ask, as we drive along a road, for instance, what's the height in meters above sea level as we travel for various kilometers, we might see a graph like this, and there again we can have a secant line defined, and the units will naturally come out of the meters in height, and if you want you can get a little more specific, over the units of kilometers for the horizontal travel. So we could talk about how many meters we've gone up or down per kilometer traveled on average, because we'd be talking about the slope of a secant line. Finally, let's take a look at this last graph and ask yourself for a moment, what would the units of a secant line of a sales or demand against price curve look like? These curves typically have this kind of shape. And if we were to identify the slope of a secant line connecting those 2 points, what would the natural units be? Well, fortunately we can apply the same logic we had before, which is we're going to have the change in sales divided by or over the change in price. And so the units would be 1,000 units. K units is typically a short form for thousands of units per dollar of price. And that would be what we'd get as a measurement of the secant line slope. If we found this slope, it would tell us how many thousand units do we expect to lose for every dollar that we increase the price. With that in mind, let's take one step further and compare our secant's 2 derivatives. The derivative has a lot of the same flavor as the secant line. And the idea is we had the average slope for the secant, but the derivative is one step further. We take that average slope and then we let the delta x approach 0. So imagine a curve. We have 2 points with the delta x here, but then as we have the same curve and we gradually pick one of the points to be the important one, and we move the other point closer and closer, so our delta x becomes smaller, then eventually we should end up with a point on a curve, and if the limit operations work the way we expect, we should get the slope of a tangent line instead of the slope of a secant line. And so that's what we get when we talk about the derivative. We can also talk about it in other words that get used in the scientific and economic communities. Instantaneous rate of change, so instantaneous as opposed to average. And If our function is of position, then we get velocity, and if our function is velocity and we take its derivative, we get acceleration. Notice in these ones here, there's no average involved. It's simply position's derivative is velocity. Velocity's derivative is acceleration. This indicates there's a difference in how we interpret secants versus derivatives. One thing secants and derivatives share in common, though, is that they both represent slopes. For example, if we had a velocity graph like this, and we pick a single point, and we ask, what is the slope of the tangent line? Because we're talking about slopes, again, we're talking about rise over runs. There we have meters per second in the vertical side, and we have time in the bottom. The units for this will be meters per second divided by seconds, rise over run, and that'll be meters per second squared. So we get accelerations again. The same thing is true if we're talking about driving along a road at a certain height over certain kilometers of travel. We're going to find that the units are the same as for the secant because we're still talking about slopes. We draw a line and we talk about the slope of that line. Likewise with sails, if we take a point on this graph, draw a tangent line to it, we can talk about the slope of that tangent line, but the slope of the tangent line is going to have units here, thousands of units sold, more generic units, per dollar of price. So that is identical to what we saw with the secant lines, going back a page. All these units here are the same as the derivative. The subtle differences are about whether we're talking about average or instantaneous rates of change.